In this video we're going to cover rounding. If you get into the resources section you'll find two files. We'll have the Logisim file and also the Excel spreadsheet. So if you go ahead and open up both of those files. Now you'll note in the Logisim file we can head up into the top level, and the top level is exactly the same as the previous build, there's not any change. So we head back into the next level. Now you can see here that we've added in an extra section here. We've got a sticky bit and we've also got a rounding section at the bottom here, and there's also a change in the shifter. But let's go into the sticky bit because it's the easiest one to understand. So you can see here we get the output from the shifter goes into the sticky bit, but we'll show you what that output is just in a minute. So you can see that we have the 23 sticky bit inputs. We're going to order them all together and we're going to take a single output. Now we said that if all of these values here are 0, then we know that we are exactly at the halfway point. So for example 5.5. So that means that the value here, which we actually call the round bit, whenever it is a value of 0, we know that we are at the halfway point. But if any one of these goes high, then we're not at the halfway point. So this is the sticky bit, and it's quite a simple part of the rounding section. So let's continue. Now we're going to get into the shifter, and there's a couple of extra sections in the shifter. And you can see here we've got this extra section in here, which we'll talk over just in a minute. And we've also got this extra section here, which I'll try and get through in this video, but if the video is too long, I'll just go on and do this on the next video. So what we said we wanted to do is we wanted to take a note of the information that gets dropped off whenever we shift the Y value. So we needed to increase the exponent value for Y. Whenever we increase the exponent value for Y, we have to decrease the mantissa in order to make the number the same number. But when we decrease the mantissa, that means we shift it to the right, then there's information gets dropped off the end, and we wanted to retain that information, and this is the method we've used to retain that information. So I'll zoom in just now and we'll have a look at this little section here. Now if you get confused, remember that you should always go in and you can add in the probes. So if you go to the wiring, you've got the probe, and you can add in a probe and you can face it, say south, and it will give you the values that are at those points, and you can compare these to what we have in the spreadsheet. So I suggest that when you're working through these examples that you do exactly that. Okay, so we'll talk through this section first. So I've added a few probes in here in order to follow the ones and zeros. Now this circuit here we've seen before. This is the shift of the my. So we shift my by the value ex minus ey, and we get our value for our mantissa out. And we said this little section here is going to capture the values that drop off the end whenever we shift this out. So if we head into the spreadsheet, and if we can put in a couple of numbers, so for example say 56.1 and 6.1, and we have a look and see, we can see that in this line here, which is row 11, we've got our Y shift. So our Y is going to be shifted by the difference of our ex minus ey. So our ex minus ey is 3. So it's going to be shifted by a value of 3 to the right. So it means this point here moves 3 to the right. So it goes to that point there. So the first 24 bits here, so the red one is the hidden bit, and then the other 23 bits are the mantissa. So these here are given by this section here. And then what drops off the end? What drops off the end is what goes into this red section here. So we're working out this point here, and you can see whatever drops off the end, in this case is 0, 1, 1, well, all the rest of the values here are going to be 0 because we've only dropped 3 digits off the end in this example. So if we head back to the Logisim, what we've done is we've taken a copy of our my, and instead of shifting the my to the right, we're actually going to wrap it around. So for example, if we were to put in a value of 1 here for our my, and our ex minus ey is a value of 1, then it'll take this 1 here and shift it round, and you can see here it's taken it and shifted it round here. So this kind of looks like roughly what we're looking for. If we were to shift this 1 to the right, then we would have all zeros here, and then this value 1 would drop off the end, and it would enter into here, and it would become the most significant bit of this lot here. So it looks like it's kind of working, but it doesn't work exactly right, because if we had for example, a value of 1 here, and we were to shift it by this value of 2, so what we want to do is we want to shift this out by 2 values, so the 1, 1 would drop off, and what we would get up here would just be the 1, 1, and then all zeros. But we don't have that because it still adds in this other value of 1 up here. Okay, so when this shifts this way, this one shifts to this position, so we're going to end up with this extra 1 that we don't want. So we don't want that 1 here, so we have to get rid of it. So we get rid of the extra values from the section below, and you can see how we're going to do that. What we want to do is we want to take the ex minus ey. So for example, in this one here, the ex minus ey is a value of 2. So what we want to do is we want to make the remaining bits after 2 all zeros. Okay, so that is we want to make the remaining 22 bits all zeros. Now if the ex minus ey was for example 3, then we would want to make the remaining 21 bits all zeros. If it was 4, then we would want to make the remaining 20 bits all zeros. So what we want to do is we want to actually take the difference ex minus ey away from 24, and that will give us the number of bits that we require to be made 0. So that's what this section here does. So you can see here in this instance we've got a value of 2 here for the difference. So it means that we want to make the remaining 22 bits here of a value of 0. Now we do that here, and it's a bit of a cheeky way of doing it, but it does work within Logisim, and of course this is not necessarily the way you do it if you were building a floating point unit and say in CMOS, but we're using Logisim here, and we just want to get something up and running and to understand the principles of our floating point units. So what we want to do is take the value here, and we're going to shift it left by 22 positions, and we're going to shift in the values of zeros. So this here at the moment is just hanging, so there's nothing here. So if I was to go in and say, for example, disconnect this point here, then you would see it actually comes up with an error. But what it actually does is it shifts 22 zeros in, but it's not able to compute this AND because it doesn't know what this input here is. But what we can do is we can negate this error here by just pulling this point high, and that's what I do with this resistor connected to a value of 1. It just pulls this point high. So rather than getting the don't know condition XX, it replaces the don't know condition with a value of 1, which is exactly what we want. We want 2 1s here and all zeros. So when I connect this here, it will change these values here for the 2 crosses, or equivalently the errors up here. It will change these by values to a value of 1. So it's a bit of a cheat, but it does work and it provides us with what we need. And then what we can do is we can take the value we have here and we can AND it with what we have above. And that ensures that in all instances we get the correct output here. So you can see here that if we were to test this out, so let's say for example we put in just some other values here, we'll put a 1 and a 1 in here, and we're going to shift it. Say we're going to shift it by 7 positions. Say that's 1, 4, so that's 4, 5, 6, 7 positions. So we're shifting this 7 positions out. So at the output there we should have 1, 2, 3, 4, 5, 6, 7. So it should be 0, 0, 0, 1, 0, 1, 1. And there we go. You can see it. 0, 0, 0, 1, 0, 1, 1. So this is the rounding output that we're interested in. And of course we've got the other higher 24 bits, which is just the shifting of the EX minus EY. So that's the basic operation of this section here. And I think what we'll do is we'll leave that here for just now, and I suggest you put some values in here and you test this for yourself and you ensure you understand how this little section is working. So thanks for listening. I'll get you on the next video. Goodbye.